Welcome back to the channel, everyone. Today, we're diving deep into the world of engineering, and trust me, you don't need a hard hat for this one. We're talking about something called loads, and how they can bend, stretch, and twist materials in ways you wouldn't believe. Now you might be thinking, loads? Sounds boring. But hold on. This stuff is the backbone of how we build everything. Skyscrapers that touch the clouds, bridges that span entire rivers, even that rickety swing set in your backyard. We're going to break down the 5 main types of loads: compression, tension, bending, torsion, and shear. By the end of this video, you'll be able to look at any structure and have a pretty good idea about the invisible forces that are battling it out to keep it standing. Let's get to it. First up, let's talk about compression. Imagine you've got a marshmallow, right? And you squeeze it between your fingers. What happens? It squishes down, gets shorter, right? That's compression in action. In engineering, compression is when a force pushes or presses down on an object, trying to compact it. Think about the massive pillars holding up a giant bridge. Those pillars are constantly being squeezed by the weight of the bridge, the cars driving on it, even the wind pushing against it. Now, materials have different strengths when it comes to handling compression. Take concrete, for example. It's super strong under compression, which is why we use it for columns and foundations. But try bending concrete and it'll crack under pressure. That's why engineers spend a ton of time figuring out exactly how much compression a structure can handle before it crumbles like that marshmallow. They gotta make sure those buildings and bridges can take the squeeze. Next, we've got tension, the opposite of compression. Instead of squishing, tension is all about stretching and pulling. Think about a rubber band. When you pull it, you're creating tension. Pull too hard and snap. It breaks. In engineering, tension forces are everywhere. Look at those massive cables holding up a suspension bridge. They're being stretched constantly by the weight of the bridge deck and all the traffic on it. And speaking of bridges, those steel cables are the perfect example of a material that's great under tension. Steel is incredibly strong when you try to pull it apart, which is why it's used for everything from bridges to skyscrapers to those ridiculously strong magnets I love to mess around with. But just like with compression, engineers need to be super careful about how much tension a material can handle. Too much pulling, and even the strongest steel cable will snap, sending those cars plunging into the water below. Not good. Chapter 3. Bending the two-faced load. Alright, now things start to get a little more interesting with bending. Bending is a sneaky one because it actually involves both compression and tension at the same time. Think about bending a ruler. The top side of the ruler stretches, while the bottom side gets squished. Engineers deal with bending forces all the time, especially when it comes to beams and supports. Think about a wooden plank placed across 2 bricks with a heavy weight in the middle. The weight pushes down in the middle, causing the plank to sag. The top part of the plank is being stretched, while the bottom part is being squished. If the weight is too heavy, the plank will eventually snap, usually on the bottom side where the compression is highest. That's why engineers choose materials for beams and supports very carefully, considering both their tensile and compressive strengths. They also have to factor in things like the length of the beam and the weight it needs to support. It's all about finding that perfect balance. Chapter 4. Torsion, the twist and shout load. Time to twist things up a bit with torsion. Torsion is all about twisting forces. Imagine holding a wet towel and wringing it out. In engineering, torsion is crucial for rotating parts like axles and shafts. The drive shaft in your car transfers power from the engine to the wheels. Too much torsion can shear materials, tearing them apart. Engineers use strong materials and smart designs to handle torsional loads. Chapter 5. Shear, slicing and dicing loads. Let's talk about shear. Shear forces make things slide past each other, like scissors cutting paper. In engineering, shear forces are everywhere. A bolt holding metal plates is under shear stress. Wind pushing a skyscraper is shear force too. Engineers reinforce concrete with steel bars to handle shear forces. Building a stronger future, one load at a time. So there you have it, a crash course on the 5 major types of loads in engineering. We've covered compression, tension, bending, torsion, and shear, and hopefully, you've gained a whole new appreciation for the invisible forces that shape our world. Understanding these loads and deformations is essential for designing safe and efficient structures that can withstand various stresses without failing. If you're passionate about construction management and civil engineering, follow me and hit that bell on my profile for more insights, tips, and valuable content. Knowledge is power.